Hi everyone, let's take a look at question 17 in sample exam 3 Chem 11. This question is about trends in the periodic table, something we learn in quantum chemistry, and specifically this is talking about ionization energies. So let's take a look at the question. It gives you 4 different ionization energy for aluminum, and just as a reminder, ionization energy is referring to the energy needed to remove an electron. So you can see that in each reaction, we're taking electron away from the original species, right? And so the first ionization energy refers to the removal of the first electron, and the second one for the second electron, and so on, okay? And so if you look at the ionization energy, you notice that it's increasing as you go from the first to the second to the third and the fourth. And that makes sense because if you think about the configuration of aluminum, let me just write it right here. So aluminum originally has 13 electrons. So it's 1s2, 2s2, and then 2p6, and then 3s2, and then 3p1. So that's the original configuration for aluminum. Now, when you're removing electron, you're going to start to remove all the electrons from the furthest away position first, and that would be the 3p electron. So notice that when you remove the first electron, now you have 13 protons and 12 electrons after you remove that, right? And then after you remove the second one, you're going to have 13 protons and 11 electrons. So the number of protons doesn't change, but the number of electrons keep decreasing. And of course, the way we think about this is we look at that equation for the binding energy, which is En equals to negative RH Z effective squared over N squared. And as you can see here, if there's more proton relative to electrons, right? In this case, you have 13 protons and you have 12 electrons. There's going to be a stronger attraction, relatively speaking. And so if there's stronger attraction to the electrons, then the ionization energy is going to be higher. And that's the reason why we see this trend of increasing ionization energy. Now, the first question asks specifically about the increase that's observed between the third and the fourth ionization energy. So you notice that there's a big increase right here. So you see in the previous ionization energy, there's an increase like from 580 to 1815, and then from 1815 to 27, that's, about 1.5. But then there's a big increase here. There's a 27 to 11,600, which is almost about 5 times. And so the question is, why is there such a big increase going from the third to the fourth? Well, if you look at that electron configuration, the first ionization energy refers to the removal of this 3p electrons, right? So that's gone. And then the second one would be for this one, third one would be for this one. But notice that for all 3 of them, the N value is equal to 3. And the N equals 3 goes here into this binding energy equation. So in other words, the denominator in that equation is always 3. The Z effective changes as the number of protons increase relative to the number of electrons, but then the N at the bottom is always 3. Now, when you go to the fourth ionization energy, which is the one that we're interested in right here, 11,600, that one now requires you to remove this electron, which is in a 2p orbital. So now the N for the fourth ionization energy is now 2. So you have a lower principal quantum number in your equation, and if the denominator is 2, then of course that results in a much bigger binding energy. So because the binding energy is much bigger, now you have 2 factors that make the electron hard to move. You have a larger number of protons, which is 13 protons, right, relative to 9 electrons. But you also have the principal quantum number being a lot closer now to the nucleus, so that makes it even stronger attraction. Okay, so that's the reason why there's such a big increase in ionization energy from the third level to the fourth level. Question B says, which of the 4 ions would you expect to have the largest electron affinity? Electron affinity is the energy that accompanies addition of an electron. Okay, so if I were to write the reaction, it would be the opposite of the ionization energy reaction. So for example, for the 4 plus aluminum ion, the electron affinity would be Al4 plus electron, making it Al3 plus. And then there's a electron affinity associated with that, right? And then for the 3 plus, it'd be this. And then there's a different electron affinity associated with this, okay? And so they're asking us to compare how this energy would be, and then particularly the one that has the largest electron affinity. So in this case, the largest in absolute value terms, right? Now, electron affinity, typically they tend to be negative, right? Tend to be exothermic. So we're just asking which one is the most exothermic here. Well, based on the idea that this is the energy that accompanies the addition of an electron, basically the one that's going to be the most exothermic is the one that can tolerate the electron the best, meaning that when you add the electron, this electron is really stable because there's a lot of protons that are interacting with the electron. And of course, that means that the best one should be the aluminum 4 ion, because that one has the most proton relative to the electron, right? 13 to 9. And then, as we said earlier, when you're adding that electron, you're adding it to the level 2, principal quantum number 2, which is closer to the nucleus, so that will make that electron addition the most stable and the largest electron affinity. Now let's take a look at question C. It says list the 4 aluminum ions in order of increasing size. So size also depends on this equation, this binding energy equation. And so if you have a very strong attraction between your valence electron and your nucleus, then that's going to make your size much smaller, right? So if it's a proton, the closer your electron is located to your nucleus, then the smaller its size will be. So that tells you that the aluminum 4 plus is going to be the smallest, because that one, the electron is located at the n equals 2. I should draw it correctly here. The n equals 2. The Al4 plus would have this closest distance to your nucleus, which is right here. So that would be your smallest ion. And then the other 3 are all located in the n equals 3. But then, so they all have relatively the same size, except that there's small changes between them because it depends on how many protons are interacting with the electrons, right? So the more protons, relatively speaking, that interacts with the electron, the smaller its size would be. So then that's followed by aluminum 3 plus, aluminum 2 plus, aluminum plus, and then lastly aluminum.